Good morning, everyone. Okay, so in today's hands-on session, we'll be giving you a brief outline of what is Laplacian form, how to set up a 1D conduction case, how to run the simulation, and some basic results and post-processing we'll show you. So first thing is this Laplacian, what we are going to solve is the diffusion equation. Okay, this is our equation, which everybody will be familiar with. Okay, so only thing is the rho Cp value we have divided by it throughout. So our right hand side is of the form q triple prime by rho Cp. Okay. So now if you want to look at how OpenFOAM solves this equation, you have to go to the source code. The source code is located at this location: cd $form underscore solvers basic and then Laplacian form. When you do that, you will be able to see this source code. So I will just show you the path of that so that quickly. So to go to that path, open your Ubuntu terminal, or if you are in Linux, just press Control Alt and T, and then type the path. So the the quickest way to go over there is just to type SOL. When we type SOL, it takes you directly to the solvers dictionary. So all these are shortcuts. Like RUN is a shortcut to go to the run directory. SOL is a shortcut to go to solvers directly. Similarly, TUT is a shortcut to go to your tutorials directory. So now I said I am in the solvers directory. If I want to know what are the solvers, I can just do ls, and you can see that there are multiple solvers over here. Now Laplacian is in the basic folder. So I will go to basic. In that, see Laplacian form is there. So I will go to Laplacian. So I think by now everybody is familiar with using the cd command, cd to change the directory. Now in Laplacian form, if you see, there is a file named Laplacian form.c. You can open that file by using your gedit text editor. So gedit space Laplacian form.c. I hope everybody is able to do this. For those who are not able to do, I think I will go back. So when you open, you will be somewhere maybe in your run directory or in your home directory. Just type SOL. After that, type cd space basic, then Laplacian, and then press enter. Now you will enter into the Laplacian form. If you type ls, there will be a file name Laplacian form.c. You have to open that. So to open that, you just type gedit Laplacian form.c. So instead of gedit, just write notepad.exe. So it will open the same file in notepad. So if you see, this is your main C file, or the main .c file that runs when you run the Laplacian. So in this, what is important to see is this section over here. So this is what you have to look at. See, the equation that we are solving is ddt of t, that means dt by dt minus FVM, that is Laplacian, of t is equal to source. So now the source we have to add using the FV models file that is available. So from the FV models files, it will pick up the source, and then it will solve this equation. So this is what is shown to you in this PPT slide. Okay. So now if you look at it, what is the if we write our conduction equation in the form that it is being solved, we see that our source term is nothing but q triple prime by rho Cp. That is volumetric heat generation divided by rho into Cp. So understanding this is important, because generally whenever in conduction somebody talks about source, you will only think that okay, source is just q triple prime. Okay, so in this case now it is not q triple prime but q triple prime by rho Cp. So the value of this quantity is what you have to enter in the source. Now if you go to the next slide, this is our problem statement. So we begin, and what we need for this is we need a simple geometry, okay, in which at the left end we are setting the temperature as 0, right end we are again setting the temperature as 0, and internally we are adding some heat source. Now the material that I've chosen for this is copper. So if you see, it has whatever the thermal conductivity, density, and specific heat mentioned. So from these values, I've calculated what should be the diffusivity. That is alpha, that is K by rho Cp value. And also what should be the source term. So source term will be Q triple prime divided by rho Cp. So Q triple prime I have chosen to be 1e6 watt per meter cube. Okay. So this is our case setup. Now, for in this, we are not going to give you the case setup files ready as it is, as we have done in the previous cases, because we also want to teach you how to uh, use some case file structure that is already there, like in this case, and then modify it so that it works for you. Because this is what you will be doing in your own application whenever you want to run. So, how do we generally begin? We want to solve a case for Laplacian form. So we should go to the tutorials folder and pick up a case of Laplacian form and then modify that, because that case will have all the necessary file structures that are needed to solve the Laplacian form. So this is the general approach. So when we wanted to solve a case for simple form, we went ahead and picked up a case from the simple form tutorial. When we wanted to solve a case for icoform, that is cavity, we went ahead and picked up the cavity case. So to copy a case from uh, the Laplacian form, we'll be using these commands. So first, what you need to do, first we are saying go to the run directory. So I'll minimize this. So my terminal is here. Okay. Now you are in your solvers directory. To go to your run directory, just type run. It takes you to your run directory. The longer command will be cd $form_run, or shortcut will be just type run. Now in this, the second command we are saying is to make a directory called conduction. So to make a directory, the command is mkdir space conduction. So it will create a folder named conduction. So when I do that, and if I do ls, you see a folder named conduction has already come up. Okay. Now, what I need to do in this, I'm creating a folder. I'm copying a folder from the Laplacian form case. So the command will be cp -r, copy the folder, and then dollar. So if you are having difficulty, Biraj will copy and paste those commands for you. You can copy it from the chat as well. And make sure that you type everything with underscore, spaces, everything properly. Form_tutorials /basic. So this is the location from where we are going to pick up the tutorial case. In that, Laplacian form and flange. So we are picking up the flange case. I'll give a space. Where I want to save it, I want to save it in my conduction folder. So in conduction, but in conduction, I will also tell you to make a case 2. That is wherein to modify something. So that's why in conduction, I will create one more, a folder named case 1. Okay, so in conduction, a folder named case 1. So when we do this, and I will go into that folder, cd conduction /case 1. To go into the folder, you have to do cd conduction. Now you're in the conduction folder. If I type ls, there is a folder named case 1 that is already created. To go into that, cd space case 1. Now we are in a case 1 directory. If I do ls, you will be able to see that there is something called as 0 all clean, all run, constant, flange.ans, and system. So now what we will do is, we don't need all these all run and all clean files.
Sorry to interrupt you. So
Yeah.
the notepad.exe Laplacian form.c it is not working afterwards.
It is not working.
I have typed the same thing, and it is showing that this folder is not exist.
So see, you have to understand Notepad. When you are giving the command notepad.exe and Laplacian form, what you are telling the system to do, you are telling the system to open Laplacian form with Notepad And where is Laplacian form? It is in the current directory. So that will only work if you are in this directory. Can you see?
Hmm.
Slash
Hmm.
opt openform 9 application
But
and then Laplacian form.
yeah,
If you are not
but
in that directory,
I
then
am
this command will
application
not.
solver. Application
Yes.
solver directory I am.
So if you don't do the commands that are there before, it will not work for you. So what were the commands that we did before? So we were in, see
Application
here,
solver basic CD
here.
file.
So as soon as I got to the solvers directory here, I went
Hmm.
to basic directory and then to Laplacian form. So if you miss these commands, it will not work.
Okay, okay, got it, got it. Thank
Huh,
you.
okay. Once you
Hello.
understand what that command is, you will also understand the error quickly.
So here we are doing one conduction folder in run directory. After that, we are creating one case one folder in same directory.
Yes.
Okay.
Okay. Yes, you all leave that Laplacian form, just close it. Okay, you don't need to. That I just showed you where the source code is, right? So that later
So,
on, if you want to see, that is not the
hmm.
agenda now. Okay, close that.
John
Go
sir,
to your run directory.
hello, John
Yes,
sir. So
yes.
whenever we miss a line or forget a line, so do we need to restart the whole thing?
No, depends where you are, right? So you have to
So, so,
follow the
so
sequence of commands.
okay, so suppose there are 10 line and miss the line 5, directly 4 to 6 I have done by mistake. So do I
Uh,
need to start from the line 1?
Now, okay, now it is not exactly like that. Depends on what those commands are. So that's why I'm saying you understand the command, then you will understand, right? It may be that, like, see, first you have done your, if you see this, if you go, the first command, you're going to the run directory. The next, you're creating a folder named conduction over there. Then you're
Hmm.
copying the contents. Then you're going into this. So there is a sequence, right? So you please follow this sequence. So that's why we have given you command sequence by sequence. If you miss anything, open this PPT. We have shared this with you, right?
Hmm.
Uh, so keep it side by side. Keep it like this. Keep the other terminal this way, and then please follow this side by side so that you don't miss anything.
Yeah, so in that command, what is the significance of flange, that word flange?
Okay. So that we don't need now. Okay, this is only if we are importing some geometry. So that's why then all those things will be needed, those extra files. So what we are doing is, see, so to quickly recap, what we have done is we have gone to a run directory. In that, I'm highlighting those commands. Okay. In the run directory, I have created a folder named conduction. Okay. Now, in that conduction, I'm copying the tutorial case from the Laplacian form called flange. And inside conduction, I'm creating a folder named case one. Now I'm entering into the folder. So don't forget this command, cd conduction. I'm entering into the folder. Then I'm entering into case one. And I'm seeing, ls means to see what are the contents. So now you see that there are other files which we don't need, like all clean, all run, and flange. So our next step will be to delete them. To delete them, type the following command, rm flanges dot ans space and then all and then star. Okay. When we do this, if you see,
It is flange, not flanges.
okay, okay, that's why. Okay, thank you. So, yeah, so when I do this, so I think all it already deleted. Yes, because all it had previously deleted. That's why it couldn't find that. So if you see, if I do ls, those unwanted files have been removed. Now, what we need to do, we need to mesh, right? So our geometry that we have, right? It is a simple 2D geometry. So its setup is similar to our cavity case, right? Its setup is similar to our cavity case. So what you need to do, you need to copy that block mesh dict from the cavity case into this. So the command for that is there in your PPT. You can type that. So I am copying the block mesh dict from my cavity case. So Viraj will type that command, so you can follow that. Cavity, cavity, and in this system, and block mesh dict. Please make sure you don't make any spelling mistakes like I did in the first one. So then, and then I am saying, then paste it in my system, right? So this command should work if I have not made anything. This tutorial input. Okay. Now if I do ls cd space system and then ls, so that block mesh dict has been copied. Okay. Now what we need to do is we need to edit this. So to edit, I'll go back. I'll just type. So my gedit is not working. I'll type notepad.exe. For whom gedit is working, type that notepad.exe. And now you want to edit your block mesh dict is in systems. You type system and then block mesh dict. So our points generally they will remain same. Only what we need to do is, if you look at the diagram, okay, that I have given over here.
What did you do after cd system slash?
Okay. Yeah. So after CD system, no, you don't need to go into system. I wanted to show you that block mesh dict is copied. Okay. You can be in your case one folder. So you go back, do CD space dot dot. So you come back to the system folder. That is your case one folder. Sorry, not system, your case one folder. And after that, you type notepad.exe space system slash block mesh dict. So
If
with this,
Notepad is not working, then we can use explorer.exe.
see, explorer.exe is to open the file system. Notepad should work for you. Or gedit, Notepad or gedit, one of those text editors should work for you.
Okay.
So we have this block mesh dict. Now this we have to modify. Yeah. So if you look at the geometry over here, so our geometry is similar to the cavity case. Okay. Only thing is the x direction is longer, y direction is shorter. Okay. And z we don't need to add much thickness. So accordingly we have changed the points. Okay. So in the x direction I've kept 1 meter. In the y direction I'm keeping 0.1. And in the z direction, let it be 0.1 only by default. So x I'm keeping as it is, only the y coordinate I'm changing for the points. Now my structure, everything remains same. Only now it will no longer be my moving wall. It will be something called as side 1. That is my left side. Okay. Side 1 will be type patch. This is the patch for the side 1. Similarly, I need a patch for side 2.
John, in my gedit file, it's coming boundary, moving wall, and then type wall.
Yes. So I'm editing those.
Okay, so I have to remove the moving wall.
Yes, so you have to remove the moving wall and rename that and change it to. So if you see in the PPT, I have shared what exactly needs to be in your block mesh dict. So you have to edit it so that it is exactly like that. If you're able to edit it quickly, that's fine. Otherwise, I will share this file with you. Okay. So I'm just trying to tell you what we are doing. Okay. That was the boundary conditions for the cavity. Now we have changed it. So all the structure, this will change. So I have made side 1. Similarly, I will make side 2. For side 2, it will be the right face. That will be 2651. So I don't need these two. I only need 2651. Okay. Now side 1, side 2 is done. Then we don't have to see like how here we had given front and back as empty. So we can do that. We can keep front and back, and also the other two sides as empty. Or a quicker way to do that will be, there is something called as adding a default patch that you have to do outside boundary and before say after edges. So you add something called as a default patch, so that whatever is not mentioned over here will have the characteristics of the default patch. Instead of adding 2 3 typing the names and giving over here, this is a much quicker way to do this. So name will be empty patch, because you can give any name, that is not a problem. And type we are giving empty, because you are not solving, this is a 1D problem, we are not solving in the say y or in the z direction, we are solving it only in the one direction, that is x direction. So you will give only two faces in the x direction, that is the left wall and the right wall. I hope this is clear. You are only giving the left wall and the right wall. The top, bottom, front and back will all be empty because you are not solving in those directions. And to quickly give that, you have to use the default patch. So that will, because of that, you don't have to add those spaces. So this will be quick. So we don't have, we are not merging anything. So this file is done. So only these were the changes.
John,
So,
one question. What is this type patch?
yeah, patch is a generic label. So whenever we create a boundary, we have to either call it like wall, patch, then there is also something called as cyclic, depending upon what is your need. So patch is a generic label which we called. It is a default label. If it is a wall,
which
then we
boundary
will call it.
condition does it correspond to this patch?
No, in patch you can give anything like inlet boundary condition, outlet boundary conditions. Those boundary conditions, they work with the general label patch.
Where will you give like which boundary condition this patch is?
So boundary condition we don't give in this file. No? This is only for creating the geometry. Boundary condition will be in your T file. In this case, it will be in your T file. In other cases, it will be in your U file, P file. Okay, this is here you're just specifying what is the type. So type for this is a patch. And for here also, this one also I think I should make it patch. Okay, so my side 1 and side 2 are patches, and default patch is empty. So just after making those changes, you can save the file. If you all are able to do this quickly, you all can do this. Otherwise, should I share this file? Please type in the chat so that I will share. But before that, let me run and check so that there is no error in that. So to run this, okay, I think I forgot to change the number of divisions. Yeah. So if you see, I have given 20 divisions in the y direction. This is a thing that was there previously. Because we don't want to solve in the y and z direction, we will give only one cells in the y and z direction. In the x direction, I want to solve, so I'm giving 100 cells. 100 is good enough, and I'm not giving any grading. So this was left. So I've done that. Okay, now let me run the block mesh command. I've saved it. Once I run the block mesh command, so it has created. Okay, so there are 99
John, we
internal
also
faces.
have to remove the end part, right? The front and back.
Yeah, I removed that already.
Oh.
I think so. I removed that already. Yes, you have to remove the front and back because we are directly giving a generic label empty. So that default patch will take care of those front and back. So here I have already removed front and back. So I'm only keeping side 1, side 2. Okay, because I need only 2 patches defined. Rest, everything will take this property of the default patch, that is empty. So this is the advantage of using default patch. You don't have to write. Okay, so I will, it is working. I will send this file to you. Now next, what we need to change. After this, we need to change the boundary condition and the properties. So boundary condition changing, to change the boundary condition, you need to open the file using the command notepad.exe space. Now boundary condition is in your 0 folder. So you have to go to 0 and then E, because you are solving only one equation, that is of temperature. So the command is notepad.exe space 0/T. So this file will open. So if you see, there were additional patches, patch 1, patch 2, patch 3, patch 4, which we don't need. We need only 2, that is side 1 and side 2. So you can delete them. Now both are, I'm calling it side 1 and side 2.
This conduction problem is 2D geometry or 3D?
No, we are solving see, as previously stated, in open form, every geometry will be 3D, right? But if you have to solve only in one direction, you give number of cells only in that direction. In the other two directions, you give number of cells as 1 only, and you define those spaces as empty. So in your block mesh dict file, if you remember, we have given only side 1 and side 2, that is left and right. The others, all the other sides we have given as empty, and we are not giving any cells in those directions. So over here now, what I'm doing is I'm giving boundary condition only to those two specific sides. So my first boundary condition is not 0 gradient, but it is fixed value. Now for ease, I'm giving a zero temperature over here. So 0 temperature on side 1 and 0 temperature on side 2. So both the places it will be 0, and we will see how the temperature at the center will evolve. So this is the change that you have to make. An internal field, yes, an internal field should be uniform 0 initialization. So the internally, to start with, everything will be 0, right? At the walls, it is fixed 0 at all times.
What does uniform signifies?
Because when you're giving say value, you want that value to be uniform throughout.
Didn't understand.
It has to be
means
uniform.
uniform mesh or what?
No. Say, like in this patch, when you are saying uniform 0, it will be uniform. There are also ways in which you can give a non-uniform value. By non-uniform,
Example.
We have a case. We have a case tomorrow, I think, wherein the velocity, say at the inlet, will not be constant, right? If you want to give a parabolic velocity inlet velocity profile, then in your whole inlet phase, will the velocity be constant?
Okay.
Are you understanding what I'm saying?
Yeah.
So in that case, it will not be constant. So there we will use something like a coded value.
Okay, constant means uniform here.
So uniform means that is something that is similar everywhere. Okay. Now, after make those changes, save the file. One last change we need to make, that is in the properties. So for that, you have to open notepad.exe. Properties is in your constant folder, and then what are the properties? Transport properties. So open notepad.exe, constant and transport properties. Over here, you just have to change the value. So I think that is the last thing that you need to do, and after that, you can run. Sorry, one more thing. You need to add the source. Okay.
So can you explain the steps after the block mesh command runs?
After block mesh command, you have to edit the you follow the PPT. Please follow the PPT. Yeah. So in your transport properties, you need to change the property. The property that we are giving is diffusivity. Okay. Now this diffusivity value we will give to the value that we have calculated initially. That is 1.15. This is for copper. 34 e raised to the power, e raised to, that is a to 10 power minus 4. This is the value that we are giving. All this is available in your PPT also. You can copy from there if you have missed. I'm just showing you what changes you need to do. So you need to do this change, just one, change the value and save it and then close. Now, next you need to edit the FV models file. But if you see in our case directory, there is no FV models file because we have copied it from the base directory, from a base tutorial case. So what we'll do is we'll copy the FV models file from a tutorial case that is already there. So I'm typing this command. You can copy it from the slides, or in the chat, Biraj will type it. You can copy this command. It is a little long command, so you all please copy it. You may make a mistake over here and then it will not work. So what we are doing is from the tutorials folder, we are going to the heat transfer case. In that there is a CHT multi-region case. CHT multi-region foam. In that there is a case called cooling cylinder. 2D and constant. So constant and then solid and then FV models. So this file that is available at this location, I want to copy it to my current location. That is, I want to copy it in my constant directory. In my constant directory. So I hope this works. Yes. So now I just want to verify that. So I'm going to my CD constant. You all don't need to do this. Okay. FP models file is there. So this is the command that you need to type. This command will be available in your chat. Okay. Once this command you have typed, a file named FP models will be copied to your constant directory. Now what we are doing is we are editing that file. Okay. So to edit that file, again we are using our, say I'm using Notepad. You can use gedit, whatever. Notepad.exe space system and then FP. Sorry. Constant. Sorry, it is not in constant. It is in sorry, it is not in system. It is in constant and then FP models. So when I open this file, if you see in the PPT, till then I will try to explain. In the PPT, this file was written to add a heat source Q. Okay. So in that case, whenever you are using CHT multi-region foam, this type of a source works Q. But it will not work for our case because our source term is different, right? Our source term is of the form Q triple prime by rho Cp. So we need to delete this and we need to replace this by some other command. So I'll edit this. You can edit this. What you need to edit is available in your PPT. If not, you tell me, I'll share the file. If you're having any problem, share this file as well. So I'm calling the name. I need to give some name. So I'm calling the name as energy source. Type instead of heat source, I'm calling it as a semi-implicit source. Selection mode all. And then delete this and write sources. I have to give source for temperature. Explicit value of 0.29. This value we have calculated 0.5372. This value that we have calculated as a unit of Kelvin per second. So this is just comment that I've added over there so that later on when you use it, you remember that this is not the Q, but it is the value of Q by rho Cp. So you can use this same case file to do some other case and maybe modify it. That time you will understand this. So it's always good to add some comments. Okay. So I'm closing this T and then I'm closing, sorry. I'll also close this sources.
You can copy this.
Yeah. So I will copy. Should I copy this whole text or should I?
The text.
Okay, I will just copy this text so that maybe you can copy paste this whole thing. Just let me verify it once. Energy source type semi-implicit source selection.
Can you please explain these terms which you are using here, semi-implicit source, explicit,
Yeah.
all these
So
things.
I've sent it to you. Okay. Yeah. In the chat, you can copy that. Now, see, quickly to tell you, there are different ways of adding a source. Like first, if you see, it was heat source. So those are some default ways in which OpenFOAM what you can say accepts the source. Semi-implicit way of specifying is it you can specify what is the explicit contribution and the implicit. By implicit, I mean whenever you give an implicit contribution, whatever value you write over there, it will be multiplied by t. So I think it is of that form, right? Like if you add, if your source is, say, if you are adding a source, say, how do I give an example? If say if your volumetric heat generation is also a function of some other parameter, right? Then it will be an implicit, like it is a function of temperature, like in this case. So then that will be in your implicit contribution. But our right now our temperature, whatever value we are giving is constant. So that goes into your implicit. You can read up more on this. So it is explicit plus implicit contribution. I think it is of the form SU plus SPX. Okay. So SP is your implicit contribution. So implicit contribution comes in whenever that is also multiplied by the source, right? Like say if this also depends on your temperature, then it will be this into T. So right now we don't need this contribution. So that is zero for us. Only so most of the time you will use only this explicit contribution. Only for very specific case. I don't know. Say in our case in scalar we can do that, but we have coded in whenever we are doing scalar because ours. Okay, that maybe I can tell you when we are doing that. So I think if I tell you now, it will just confuse you more. Okay. So this selection mode all means that you want to add this source in the whole domain. Suppose if you had only a specific part as a heater, remaining is some say solid, some fluid, something else. So in that case, selection mode, you will write the name of the heater, say like uh, a specific cell zone, like cell zone will be heater. So you will add the source only in that specific cell zone. And volume mode specific means you are adding this into the entire volume, like something like watt per meter cube is specific, and watt will be a absolute value. So this specific specifies that you are adding this to the entire volume, right? Per meter cube basis or per unit volume basis, you are adding this. That is what it means. Like sometimes you know that, say I know that my to my heater, say I provided 30 watts of heat. So I don't know what it is in watt per meter cube. So I can just specify absolute value as 30 watts. So it will add 30 watts throughout that way. Or I can give a per unit volume basis. So this is a unit volume basis. So I'm saving this. Now after this change, we have changed the source as well. Now we just need to change the start time, end time, delta t values. So you can to change that, all those things will be available in your control dict. Control dict. So it will be in your system, and then control dict. Okay. I think in the slides there is one typo over there. So L is missing in the control dict. So please, I think Veera just type this command over there so that people don't get confused. L is missing. I've made one typo over there. Instead of control dict, I've just written control. Yeah. So this is open. So now everything remains same. My end time I will maybe increase it to say a few seconds, maybe 20, 30 seconds. I have written 100 seconds over there. This solves very fast. So even if you keep 100 seconds, that is fine. Delta T I will reduce. That's it. These are the 4 changes that we are doing. We are just changing the starting time, ending time, and delta T. Okay, I am saving this. Now I can run the case. Now to run the simulation, first you need to mesh it, block mesh. So I think I've already meshed, but still I will run it. So my block mesh is done. Then to solve it, Laplacian form. Okay. So it starts to solve. So if you have any problem, the steps are also pasted in your chat. So you all please do that. Yes. So it is done. Now to view the results, go to ParaView. Now I will show the other method. So you need to type touch For those for whom the default thing is working, you don't need to do this. You can directly type parafoam. I'm demonstrating this method. That's result.foam. Okay, now explorer.exe to go to that location. So these two commands is what the people whose I can say ParaView is not working with Ubuntu. You have installed ParaView on Windows. So when you do this, yeah. So this is my folder. If you see, all the timestamp values have been written over there. Now I'll just open this result.foam. Yes, so I click on apply. Instead of solid color, I'll take T. Okay, and if I just move ahead in time, you see the temperature evolving. We can plot it also. I am unable to see this. Yeah. I'm going to my last time. So this is my last time. So to show you what I did, I went to the last time by pressing this, and I was not able to see this more clearly. So you can press this next to your T. There's an icon with the eye symbol over there. That means it rescales the color map to the current values. So this is your temperature variation. This is same as what I have shown in the PPT. Now, if you want to plot this temperature and see whether you are getting a parabolic profile or no, you can do the plot over line function that we have already shown you. So you can click plot over line. Now this is my x-axis. So here in the properties tab, I need to go and click on the x-axis and then click apply. So all the other quantities are getting typed. I will remove everything else and leave only my temperature. So if you see, I'm getting a parabolic temperature profile. Now you can save this by going to save, going to file and then save data. And file, save data, and then select the location. Select the location where you want to save it. Give a file name and file type. You can change it to CSV, comma separated values.
John,
with
after
this
selecting plot over line,
Yeah.
do we have to change any settings?
Yeah, so after selecting plot over line, I will show you again. I will delete this plot over line. Okay. So now I click on plot over line. I think part of my thing is not visible. After selecting plot over line, you have to click on the x-axis so that it plots on the x-axis. But I think you all have got the plots. After clicking, go to click.
Yeah, you have to enable the properties tab from the view. Then you can see
Why has it gone?
in ParaView.
Yeah, I didn't
In
click anything.
ParaView itself, your properties tab is not visible. That you have to enable.
How did it get disabled? That maybe I clicked somewhere.
Yeah, in view tab.
Yeah.
Property.
Why is it? Okay. Yeah.
Yeah.
It is getting
There we can.
okay. Yeah. So here you can see that
Now you have to select
after
the plot over
yeah.
line.
So you see now this is your temperature. If you initially select, you will get something like this. If you go to your last time step, you will see something like this, right? Wherein you're not able to see the full variation. Now, if you click on rescale, it will rescale the data for the current time step so that you see the variation. Now you have to click on plot over line. If you see over here, you click on plot over line. After this, it will arbitrarily take a point from this, what you can say, one corner to the other. But if I want it along because my variation is only along the x-axis, so I can click on x-axis over here. Once I do that, I need to click apply. And then I will get this. So I'm getting some other properties also which I don't want. So I'll uncheck all of those. And I will see only the temperature. So this is the temperature profile that I'm getting. You can save this, save it as give whatever location you want and save it as CSV file. So these things are what you need to do. Then after you do that, so what I've also done is, after I've extracted that data, I have compared it with the analytical solution. This solution is available in Intropera, right? So the orange one is my simulation results, black one is analytical. As you can see, it is a very good match. Okay, so this way you can also verify. Now, as an assignment, what you can also try to do is, after this, try to change, like we have given both the end temperatures at 0. So keep one end at 0, maybe keep one end at say 5 or something, and then see how this profile will shift. Or keep the other end at 1 first, and then see how this changes. Maybe change the heat source value, increase the Q value. But you need to do this calculation to know that if I increase my Q value, what should be my source term. So this is something that you have to calculate. So this will be an assignment for you. I think with this, we have finished our first session.